Hey everyone, welcome back to Pine Hollow Auto Diagnostics. Today I'm actually helping someone out, a YouTube subscriber, at his shop. We're working on a 2010 Chevy Equinox with a 2.4 liter direct injected engine, and it's setting 3 trouble codes. And here they are. P0011 intake cam position system performance. Okay, and then we have a 0089 fuel pressure regulator performance, and 228D fuel pressure regulator 1 control performance. Alright, so 3 codes. I don't know if they're related or not, so I guess we'll just pick one and run with it. I guess we'll start with the first one, the P0011. So what is this code all about? Let's take a quick look at our troubleshooter. I do love this big screen. Maybe I should set something up like that in my shop, because for videos this is pretty fantastic. So code tips P0011. Let's see what the Verus has in store for us today. So, control module has enabled the CMP actuator. Check to see that the vehicle has the proper oil viscosity, engine oil level, etc. Check each actuator solenoid valve assembly for damage. Check the resistance. We have a resistance spec, 8 to 12 ohms. With ignition on, measure the battery voltage between the CMP actuator solenoid control of the affected actuator and the ground. If less than battery voltage, test the cam actuator control circuit for an open short to ground. Okay. If all circuits are okay, suspect the ECM. So it actually gives us a little functional test. I guess we can see what that's all about. So you want to start it up, Jim? Says set parking brake, block drive wheels, start and idle engine. Alright, car's running. Click continue. You hear the idle raised up a little bit there. And here we have some data. So here we can actually test the intake cam actuator in degrees. So we'll start the test. Output control not allowed, DTC is present. Well, that's silly. If we have a DTC for this thing, we can't do the functional test. Alright, yeah, that's cool. Let's exit out of here and just look at some live data, what we have right now. And we actually should have a CMP actuator data list. Alright, here we go. We got exhaust angles 5, desired angles 5, that one seems good. Intake angle 0, desired is 0. Command is 0, everything's 0. Okay. Wait. You want to just rev it up a little bit, see if we get a change in command, Jim? Yeah, just hold that at like 2,000. Custom. We just want the intake and exhaust. Alright, bring it back down. Huh. So, I guess I didn't want to command anything now. I don't know if that's because the code is set right now, or what. We can try clearing the codes and seeing if we can do that functional test. We can try a functional test here. CMP actuator tests. So actuators and solenoids. And let's see, exhaust, intake. Okay. Let's see if it'll let us in. Nope. Nope, can't do it. So let's try clearing the DTCs while the vehicle's running. Now usually you don't clear DTCs right off the bat, but you know.
Sometimes they don't pop right back out, so you clear them.
Okay. So let's do clear codes. Okay. Codes menu. Wow, what's this? 341, that's new. Intake cam position sensor performance. Position sensor performance. Well, that's interesting. So let's try that test again. It might kick us out because there's another DTC. Cam actuator tests. Intake. Okay. Raise the idle. Again, we have all zeros on the intake. Test. No. You said you had it in there before. Is that right after clearing codes you got in it?
Yeah, you can try it again.
Yeah, okay, let's see. So keep that in mind. We have the 341 right now. It's clear. Okay, continue. Check for codes again. Ooh, no codes. Let's hurry up before it decides to crap out again. Actuator, intake. Okay. There's still zeros. Start the test. Oh, really? I wonder what it's at. Let's see, codes. Holy mackerel. So it said the first three again. Alright. Interesting. So at this point, since we can't do the bidirectional test, let's pull up a wiring diagram of these camshaft solenoids, actuators, sensors, etc. and get a scope on there and see what we have. So actually, the other code, now we have a P0016, not a P0011. Crankshaft position, intake camshaft position not plausible. Interesting. So it was actually a different code than before, and that's it. We had just have those three. Let's just scan it again just to make sure. Yep. So wiring diagram. It looks like we have a camshaft position sensor on the intake, camshaft position sensor on the exhaust, and then a crankshaft position sensor. And then we have a camshaft position actuator solenoid valve intake, and same on the exhaust. So this should be everything we need. Let's just keep scrolling through, make sure we didn't miss anything. Okay, so on the wiring diagram, what's the game plan? We'll hook up the Pico. Want to hook it up to our signal wire on the camshaft position sensor intakes. That's the orange wire, right? Camshaft position sensor exhaust, dark green wire. Take a look at those, get a cam crank correlation, maybe throw the crank in there, why not? So that's 3 channels. Then these solenoid valves they look like both sides, the power and ground side, are tied into the engine computer, so it can actually, you know, switch the power side and switch the ground side. So it's kind of not just a simple power or ground side switch solenoid. So again, we can probe either or. We know the exhaust valve is supposedly good, so we can get some known good signals from there and then move on to our intake. So let's set up the scope. Alright, so this is the first setup with the Pico. 4 channels. Channel 1 is camshaft position sensor intake side signal. Channel 2 is on the exhaust. Channel 3 is on the crank sensor signal. And channel 4, I picked this pink and black wire, which is the cam solenoid valve on the intake. That's the power side, you know, the positive side. We could try white and black on the exhaust side because that's a known good. I'm actually thinking that's what we should do first. Let's go over here, that side. Okay. So, in our initial signals, key off is channel 1's at 0, channel 2 is at 5, channel 3 is at 5. I don't know why this computer's not asleep. Channel 4 is at 0. I don't know, let's start it up, see what things look like. Oh, where's that ignition key? Right here. There's a weird crank. You don't even hear it crank, it just kind of starts up. Alright, we got some stuff. Let's see, channel A looks like it might be disconnected. There we go. So we got signals, alright. We can stop that capture. Shut it off. So this is where the touch screen comes in handy. You can just kind of zoom right in. And what do we see here? That is some funky stuff. Question is our ground good for our scope? And that stud might not be a good ground. So let's relocate. Oh, see, my alligator clip wasn't even plugged in. Let's try that again. I guess you can start it up. Jim will see what our signals look like. Okay, that makes more sense. 0 to 5, and then our channel D, we can drop the scale. There we go. Here, rev it up, just give it like a snap throttle. Okay, that's good. Shut her down. Okay, let's save that and see what we can figure out here. So this is interesting. So intake, exhaust, crankshaft position sensor, and the duty cycle control on the positive side on that exhaust solenoid. Now, as we saw in the scanner, it was about 50% duty cycle, and that's exactly what we see on our scope. So that matches. Now, cam and crank correlation. Is this good? Is this bad? I don't have a known good waveform at idle at the moment, so we're just kind of gathering data and seeing if we can change these, you know, based on our command from our scanner or from the engine computer. So, you know, we can get a degree measurement, like, you know, should these line up at idle? Maybe. So potentially, you know, this could be bad timing, absolutely. But we do know that our actual signals are good. You know, the cam and crank signals are there, they're clean, you know, 0 to 5 volts, and the command is there on the exhaust. So, you know, this, we're just gathering data here. So let's pull in some cursors for degree rotation. So let's say from there to there, that's 1 revolution of the crank. You can see the sync notches, and we can actually let's see, how do we do this? Should we say 360? That's 360, right? I know Jim's gonna want to buy a picoscope after he sees me using this. He already said so. So that's 360 degrees. So now we can say, okay, that step should potentially line up with that step right there. Right? You know, you would think maybe they should line up at idle. And the difference between our two cursors right there is 53 degrees of crankshaft rotation. That might be good, that might be bad, but we'll write that number down, and if anything changes, we'll be able to you know, compare it to this waveform. So next step, I want to move our fourth channel to the intake, you know, the suspected bad side, and see what the command is on there, and see if the scanner or if the computer is actually capable of controlling it. If we reset the codes, if momentarily it tries to do something, and I'll try to catch that on the scope. Okay, so this code P0016, crankshaft position, intake camshaft position not plausible. That kind of worries me, and our scope pattern, you know, could potentially show a timing problem on this intake camshaft. So let's back out of here and look at the troubleshooter. Again, not the best place to look, but just to see what could cause this P0016 code. So when the ECM detects that the intake sensor pulses occur less than 9 or more than 12 crankshaft degrees outside of the normal position, less than 9 or more than 12 crankshaft degrees. And what did we just calculate from the pico capture? Those intake camshafts were, what, about 54 degrees, you know, out of sync, or potentially out of sync. We still need a known good waveform at this point, but that could definitely set this 0016 trouble code. Let's see, 25, 35 engine cycles. Inspect the engine for any recent engine mechanical repairs. Incorrectly installed camshaft, crankshaft timing chain can cause this DTC to set. Check the intake actuator for binding or being stuck. Okay, that's great direction. Again, to do any of these bidirectional tests, we need to clear the codes. We can try that. So with key on, engine off, I clear the codes. Obviously there are no codes present, the vehicle's not running. Let's start it up, and the only thing I moved over here on the scope leads, now we're on the intake solenoid positive control side. So again, scope's rolling, start it up. Oh, that's interesting. It actually tried to command it, and then it stopped. I think our waveform should be very informative in this case. And what's going on with our fuel pressure here, Jim?
That's okay.
That's okay? Okay. Let's see. Shut it off. Key back on. Turn these lights off so they don't kill the battery. And scan for codes again and see which one we got. By the way, this vehicle has how many miles on it?
179.
179,000. So pretty high mileage for a 2010. And there you go, 0016. That's the only one that popped up there in the short run that we had. And again, let's save this waveform and take a look at it. So this is really pretty neat. You can see on the intake side, that control wire, it tried to do something right here. What did it try to do? That is a weird waveform. It tried to energize that solenoid for sure. Now look at our correlation again. Our intake is, you know, advanced with respect to the exhaust. We can put in more cursors, but you know that probably didn't change. I want to measure the resistance of this intake solenoid because we have a known resistance spec. We have a one, you know, the neighbor next to it, we can compare to that just for reference and see what the heck this is all about. I don't know if this is a known good test sequence, or you know, if the solenoid's shorted or something. Maybe it's, you know, trying to limit the current. But this solenoid was, you know, just recently replaced in attempts to fix this problem, and nothing changed apparently. Now it's not an OEM solenoid, so again, let's do the resistance check just to be sure and see what this waveform is all about. Alright, we got the voltmeter out and our AES wave adapter kit, which again saves the day. So on the intake solenoid, our resistance is 13 ohms. Fantastic. Let's go to the exhaust side. See, slip these guys right on there. About 12.7, so they're both, you know, in spec resistance wise, so that's definitely not the PCM trying to limit the current. I think it's just trying to get that camshaft to move, and it's not moving. We can actually see if it's moving by looking at our camshaft position traces. So, you know, right here we're not actuating anything, and the intake is, you know, that far. I guess we can put in some cursors. How do we want to do this? So let's do the same degrees of crankshaft. Let's see. Oh, okay, there's a 0. There's 360. So just pick any two crank sync notches. So that's our, you know, 360 degrees. And now the degrees advanced that we think that this intake camshaft is about 50 degrees. That's about what we had last time. Okay. Now, as our solenoid commands this camshaft to turn, our position, you would think, would change. So we can get our cursors again. Let's go from here to here. Again, about 60 degrees. You know, it's we'll get a little better. About 54. So the camshaft definitely did not move. Now, okay, we're getting somewhere. The question is the solenoid mechanically moving? You know, opening, closing an oil passage. That's still one variable. But the way this thing cranks, it does not sound like a normal cranking you know, sound. It's kind of like so I'm thinking we're heading towards a timing problem here. Another neat thing we could do, since the coils are accessible here, pop out a spark plug and install our custom homemade pressure transducer and see if there's anything messed up with, you know, the waveform. And if the intake cam is advanced, we should definitely be able to pick that up on our pressure transducer. And we'll also get to see a peak compression number. So that might be the next step. Let me gather my thoughts here, and we'll think of what to do next.